Yo, what is up, guys? Welcome back. I think episode 117 today. We're going to take a look at Pokemon of the day. So we got a Seadra, which is the evolution of Horsey, which is what we had yesterday. Seadra Pokemon. Let's take a look at the sound. Jeez, man, it's way too loud for me. Let's jump over to this one. There we go. There's our sound. Let's take a look at our problem of the day today. Got an easy problem today. Take a look. Got a pretty low acceptance rate. 2,900 longest unequal adjacent group subsequence 1. We're given a string words and a binary array groups worth of length n, where words I is associated with groups I. Okay. Your task is to select the longest alternating subsequence from words. A subsequence of words is alternating if for any two consecutive strings in the sequence, their corresponding elements in the binary groups differ. Essentially, you are to choose strings such that adjacent elements have non-corresponding bits in the group's array. I'm a little confused what that means. If this is what I'm thinking of this question, I think this question is really stupid. Like, what a great description to say English. Every word is either red or blue. You need to select a subsequence such that two consecutive words have different colors. So I think that's kind of what I was thinking. So I think we have to select a subsequence here where, well, the binary of 0 and 1 have to be different. So it could be like, there can only be two here because it could be 0, 1. So it can be either EB or AB. Okay. Trying to think here. Well, what is the best way to do this? Can we like I don't know what the best way is to do this array string dynamic programming greedy. It's a DP problem, really, bro? So obviously we're gonna have to return a list, right? So I'm gonna create an array to return, right? My initial thinking here, I was not thinking DP. I was just kind of thinking of like a flag sort of thing where like, you know, if we have, because we have two numbers, we can use a flag, like a true or false flag. If it's true, we know we're at 1. If it's false, we know we're at 0. And then we can, because the size of groups and the size of words are the same, we can just like add the index to the list. I'm gonna try that first, right? That's my initial intuition. I don't know if that's correct. Some sort of flag we could start at. Probably need some sort of if statement to start, like if groups 0 is equal to 0. If we have to initialize our flag, we can leave it started at false actually. Flag else groups 1, so group 0. Else then the flag is true, right? Let's do 0 is true, 1 is false, right? Okay, so we check the flag, right? Then we want to loop, right? So depending on what our value is, I guess we'd have to append actually. We'd have to do, well, res.append groups, sorry, it would be words 0, right? Res.append words 0. Okay, we loop through, line range length nums, right? We want to go from, we want to start at 1, go to the length of nums, right? So then if we do, okay, well, if groups I is equal to 0 and flag is equal to false, then I think we're gonna have 4 different ifs here. So if group size is equal to 0 and our flag is equal to false, then we want to just continue, right? Because then we found 2 in a row that are the same, right? We need a 1 here. Okay. So then we do, okay, well, else if groups I is equal to 1 and flag is equal to false, then we do res.append, flag is equal to true, res.append groups I, words I, right? Else if groups I is equal to 1 and flag is equal to true, then we just want to continue, right? We can actually get rid of this here, I think. Then we need a final else. It would be, well, if our, it would be, we would do, okay, well, our flag is equal to false. Else our flag would be false, right? Let me do res.append was we would simply return res. Nums is not defined. Okay. I wonder if this will work. There we go. Take a look at the solutions. Who's this guy, bro? Let's go, dude. Okay. Fair enough. Let's take a look at some of Leetcode's problems today. Oh. Got 1DP. It's just high end queen's problem we haven't done, I think. Oh, is that? That's backtracking. Whoops. 2DP. This time. With cooldown. Okay, so you're given an array of prices where prices I is a price of a given stock. Find the maximum profit you can achieve. You can complete as many transactions as you like. Buy once, sell. But the following restrictions: after you sell your stock, you cannot buy a stock on the next day, i.e., cool down one day. You may not engage multiple transactions simultaneously. You must sell the stock before you buy again. I'm trying to think here. Cooldown probably wants to be the most expensive day, I think, right? It's kind of the way I'm thinking about it. It's some recursion. You either buy on the first day, or you wait till the next day, or you wait till the next day. Actually, we start at I. We probably need some sort of like profit. Does everything need to be filled up though? That's the thing. That's what I'm a little confused about. 309, best time to buy and sell stock. How should I go about this? My intuition is to buy. Type of girl that wanted to chew up on my bubble gum. Damn, dude. I don't know how to do this, man. Well, I know the base case would be, well, if I is greater than the length of profit, right? Then I think we should just return. I don't know. I feel like we'd have to probably do something here. Right? Otherwise, man. It's 3 because we buy here 1. We sell, we're at 1. We cool down. And then we sell again. That's why it's 3. So we need to keep track of some sort of like some sort of profit. Hold is gonna be like a boolean. Let's do, okay, so okay, we do backtrack. We start at 0, we have a profit of 0, and our hold is false, right? So then we come in here and we do, okay, let's say we want to buy, right? So if we want to buy, then we would do okay, let's do if hold, right? Else. So if we're holding, right? So holding would be if we're like, we've bought a stock, right? So if we've bought a stock, then we have to backtrack. We pass in, we do I+1. Do I+1. Okay, to go to the next one. Then we decrease our profit. So our profit would be profit minus price is I. Okay. And then we'd be I feel like we'd probably need some sort of like cooldown or something, right? Cooldown false. Price is I, right? We would switch this to false, okay? And then we would switch this to true, right? Otherwise, if we're both false, then we would do, okay, well, I+1. Profit plus price is I. Okay, we switch this to true because we have a stock. And we're not holding yet, right? Actually, I don't feel like we need this cooldown state, actually. Because can't we just... So if we're holding, we backtrack I+1, right? Because this is where we're going to get rid of it. We would just skip 2. Right? Because we would skip the cooldown state. The cooldown state, it doesn't matter, right? Because cooldown state, we do nothing anyway. We just move over the value, right? Once we get past this,
You're back, bro? Bro, I was bored the whole fucking week from literally Monday to today. But today now is gonna get kind of busy because I'm meeting with Eva and then I'm teaching tennis the whole afternoon. Same for tomorrow, I'm teaching very early morning and then I'm teaching in the afternoon starting at 3 p.m. But I'm down to hang out like early next week, like every day literally. But especially in the morning because in the afternoon, as soon as it gets to like 3:30 p.m., I start teaching. Trying to make a bit of money, bro. But even this weekend, we can do something if you want. I think Saturday is kind of open for me. Sunday, I'm gonna teach a lot as well, so let me know. Monday, I don't have shit, so maybe we go play some golf. I don't know. Whatever you think, bro.
Here we probably need to check out the price, right? Because our profit, we'd probably have to maybe have some sort of function, non-local res, right? Some sort of res that can do like res is equal to the max of res and our current profit, right? I don't feel like this is turn res. I don't feel like this is the for given. Whoops. What am I doing wrong here? Ooh, I'm close, dude. Damn. How the hold state is being used. Keys hold should indicate whether you're currently holding a stock, but in your logic, when hold is true, you're buying instead of selling. Wait, am I? No, I'm. When hold is true, if hold, I'm selling. What is this talking about? Oh, selling would be plus. Oh, geez, yeah. Whoops. Jeez, man. Okay. Let's get rid of this and rethink about it, right? So we would do backtrack if hold, right? So if we're holding a stock, we would want to do I plus 2, and we would want to do the profit plus or equal to prices I, right? And then switch this to true, because now we're holding a stock, right? So then we would backtrack I plus 1, profit plus or equal to prices I, and then we would move to make this false, right? But this would be minus, I think. Because if we're holding a stock, we want to sell it, and then we get the price of that, switch it to true. Rock your body, rock your body, rock your body, rock your body. If hold. So we're holding a stock. We have a stock, right? We want to sell it. Right? We sell it. We move 2 though. We sell it, move 2 because we skip 1. We add the prices. Okay, now we're false, I think. And this is true. So if we're holding a stock, right? Okay. We would I plus 2 profit plus prices I. We're holding a stock. We sell, we gain the profit. We switch it, we're not holding anything. Right? So what am I doing wrong here?
nothing. Here's what's wrong. In your backtrack, I profit hold function, you're making only one choice. If hold is true, you sell. If hold is false, you buy. Okay, so this is sell. This is buy, right? We return our res, but we need, what we're missing here is a do nothing. I didn't think about that. Option 1, do nothing, right? We sell. Option 2, sell. Option 3, buy. Right? So when I do nothing, what do we want to do? Well, we would backtrack, go 1 day, we keep our profit the same. I guess we'd probably be false, right? Oh, I'm sorry, we keep our hold. Okay. Okay. So here's our brute force solution. There we go. We just missed out that option. Damn. Now we have to think about the recursive solution. Sorry, the nearly passed. 2.7 out of 210. Which I think we can add. I mean, this is a 2DTP problem, but I think I'm more comfortable adding memorization, right? So we would do our non-local res. But how would we do this? We'd have to keep track of definitely the hold, right? The sort of day it is, right? And we'd have to keep track of okay, so let's get rid of this. So we have our base case, right? Okay. DP, right? So I guess if I and then our hold is in Memo, then we would return Memo I hold. Okay. We would hold our profit, right? Option 1. Okay, we were right with the I hold state, right? The key would be a tuple. We were right about that. We get rid of this, right? Okay. If I hold in Memo, we would return, right? Option 1, cool down, right? So then let's add our cooldown is equal to this, right? And we have our sell is equal to this, and our buy is equal to this, right? So I'm thinking maybe we're gonna need to add some sort of adding the answer to all of these, or maybe we do some sort of max, maybe. Yeah, the max. Okay. So we would do a max between, so we would do, okay, well, Mimo I hold is equal to the max of cooldown and sell, right? And we have to do Mimo buy is equal to the max of cooldown and buy. And instead we would have to return, well, return Mimo sorry, this is meant to be hold. Whoops. We would call the backtracking function. We would have to return that function though. Rock your body, rock your body, rock, 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 rock your body, rock your body. Okay, we're messing something up here. I hold is equal to cooldown sell, cooldown buy. Okay. I guess we can get rid of profit too. Maybe not. Okay, we do. That's our issue. We have to remove profit. So we would go. We do profit I plus backtrack. Oh, this would be a minus. Whoops. Invalid syntax. Whoops. Do a hold here. Surprise this dude. Jeez, man. Now what's wrong? We're gonna expect it to output 1, expected 0. I don't know. I'm not sure what's wrong. You're not 100% there, just one. Mine is incorrect because when you buy, you spend money, i.e. Apparently we need to do one subtle change here. There we go. Interesting problem. Come on, come on, come on, rock your body. Come on, rock your body. Come on, come on, come on. I do feel that, like, with the DP problems, I think my intuition is better with the memoization techniques. How to think about it. I feel like I believe, ow. So memoization is a top-down dynamic programming. I definitely feel a lot more confident with the top-down ideology instead of the bottom-up, which is like the tabulation, which is like doing it iteratively. Main cost to connect all points. Let's take a look at that one. You're given an array points representing integer coordinates at some points on a 2D plane where points I is equal to xi, yi. The cost of connecting 2 points xi, yi, xi, yj is the Manhattan distance between them. Okay. Where val denotes the absolute value of val. Return the minimum cost to make all points connected. All points are connected if there is exactly one simple path between any 2 points. So I'm thinking boom, 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 boom. Nine, 3, 4. It's either Prim's or Kruskal's algorithm, I think. Used to find the minimum spanning tree of a weighted undirected graph. Okay, so it's Prim's.
It doesn't matter what your goal is, making a resume, writing an essay, or drafting a cover letter, Grammarly takes your writing game.
Continue in this manner each time picking the smallest edge that connects to an unvisited node. Notice that this
Okay, I remember watching that video a little while ago, but maybe it could be Kruskal's actually. Trying to think, we start at 0, and we go to. Oh, so we start at 0, then we move to 2. Okay. So my intuition here, without an actual algorithm, which I feel like is a little bit too basic, considering people are saying that this should be a hard problem, would be looping through this, gathering the tuples, right? So we start at 0, we keep track of the value before it. We add it here, and then we add it to our count, right? We do our distance formula, which would be this, and then we add it to our count. And then we keep track of this one, move to this one, keep track of this one, move to this one. But is it in this way? I don't know. 312. -2. 5, which would be like over here. -4. This is what I'm confused about. All points are connected if there is exactly one simple path between any 2 points. But I feel like the way I'm kind of explaining it is a little bit too easy, just using like a simple for loop and keeping track of value before it. Why my intuition falls short. If you just connect each point to the previous one in order, so you're forming a path, not a minimum spanning tree. That can easily produce a suboptimal total cost. The problem actually is this is a minimum spanning tree problem over a fully connected graph when nodes is equal to each point edge weight. You need to use either Prim's algorithm recommend for this problem or Chris's algorithm primary key plus you find. What is the difference between Prim's and Kruskal's algorithm? Rock your body, come on, rock your body, rock your body, come on, rock your body, rock your body. It's so catchy, the song, man. Build the MST by connecting the cheapest edges first. Grow the tree from a node.
see who created Prim's algorithm. It's probably his name is Prim or something. Prim's algorithm was initially developed in 1930 by Czech mathematician von Janek. Later in 1957, computer scientist Robert C. Prim and Dijkstra rediscovered and republished the algorithm. Robert C. Prim. Academic advisor. God, man, they just keep going, the academic advisors. God, man, more academic advisors. He was born in 1850. Dusseldorf. Influence gene. It's a psychologist. It's crazy, man. Anyway, get a little bit too deep and everything. 2DP. Let's take a look, see how we can implement it. 1584 main cost to connect all points. Connect all points. Let's take a look at the video. Ooh, it's a long video, but
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve minimum cost to connect all points. And surprise, this actually is not a problem from the blind 75 list that we've been working on recently. And the reason I'm solving this problem is because honestly, it actually should be a part of that list. Like, this is one of those problems I think that's missing from the blind 75 list. Reason being is this is a problem related to minimum spanning trees, a concept that a lot of people skip over, I think, when they grind Leetcode. So this is what we're going to be doing today, and you might have heard of an algorithm for minimum spanning trees. There's actually a couple, Prim's algorithm, and there's also Kruskal's. We're going to be doing Prim's algorithm because I think it's easier to implement and it's actually more efficient most of the time. And you might remember this algorithm from college. Most computer science curriculums do teach it, but if you're anything like me, you probably forgot it the instant that you finished the class that you learned it in. But that's okay. And this algorithm, Prim's algorithm, is actually not as complicated as you might expect. So we're just given a list of points that represent some coordinates on a 2D plane. So for each point, we're given two values, the x coordinate and the y coordinate. So the cost of connecting any two particular points, like let's say these 2 points circled down there, the cost of connecting them is just going to be the absolute value of the x difference plus the absolute value of the y difference. So it's actually not, the cost of connecting them is not going to be like the diagonal. It's going to be the x distance and the y distance. In other words, the Manhattan distance, if you've heard of that term. That's pretty easy to calculate, good for us. And for the entire set of points, in this case we're given 5 points, we want to know what's the minimum possible cost to connect all points. And they also say that any pair of points is going to be connected by exactly one simple path. I think that information is actually redundant. Just saying that we want the minimum cost to connect all points pretty much tells you this is going to be a minimum spanning tree problem. So the only question is, where the heck are the edges for this graph? We're only given points, right? But they do tell us pretty much what an edge is going to be, right? With the cost of each connection is just going to be the distance. So we have to create our edges ourselves. So basically, all possible edges could be, every single point to connect it to every other point, right? That's going to be a set of edges, and we can continue that. So for example, this point to connect all the other points as well. So we're going to have to kind of manually create the points. So for each pair of points in the entire graph, we're just going to take the Manhattan distance between them and just call that an edge, and then, have our list of edges, or basically we're going to create an adjacency list. So that is kind of like the pre-work we have to do. That's step one in this problem, creating the edges. But as soon as you create the edges, this is literally just a problem that you can go ahead and take Prim's algorithm and just apply the textbook definition of Prim's algorithm to this problem, and you will get the optimal solution. And the time complexity of that is going to be n squared log n, because n squared is going to be the number of edges we're going to have, right? Because to connect each pair of points, we could potentially have n squared edges, where n is the number of points that we're given, and log n is going to come from Prim's algorithm because we're going to be using a min heap in this problem. So it's pretty similar in a way to Dijkstra's algorithm, Dijkstra's minimum path algorithm. If you are familiar with that, Prim's algorithm is pretty similar to that. So let's jump into it. So
our series is about a family who adopted a child.
This is Natalia.
Are you gonna be my mommy and daddy?
We sure would love that if you'll have us.
It was a really compelling story that became a huge media sensation.
Worker.
It seems as if this could be a beautiful marriage for all involved.
Prim's algorithm algorithm is an algorithm to find minimum spanning tree. So there's a few concepts you have to be familiar with to understand Prim's algorithm. To obviously, you need Prim's algorithm to solve this problem efficiently. So I'm just going to give some of the background in case you don't know it. So basically, let's say you have a graph, and in this case, we have a graph with 5 nodes or vertices, right? And to connect all of these nodes together without forming a cycle, so we want every node to be connected together, but we don't want to form a cycle. How many edges is it going to take us to accomplish that? It's going to take exactly n minus 1 edges. So if we have 5 nodes, it's going to take exactly 4 edges to connect all of them together without creating a cycle. Because take a look right now, I can take us to accomplish that. It's going to connect all of these nodes together without forming a cycle. So we want every node to be connected together, but we don't want to form a cycle. How many edges is it going to take us to accomplish that? It's going to take exactly n minus 1 edges. So if we have 5 nodes, it's going to take exactly 4 edges to connect all of them together without creating a cycle. Because take a look right now, I have 4 edges, right? If I add another edge that's not a duplicate, if I add an edge here, we create a cycle. If I add an edge here, we create a cycle. If I add an edge here, we create a cycle, right? That's just kind of something you know, and I think it intuitively does make sense because, you know, if you start out with 5 nodes, you add 1 edge. Now we have 4 different, you know, connected components. We have one here, and then a couple here. Every time you add an edge, you're decreasing the total number of connected components by 1. So if we start out with 5 nodes, we add 4 edges, we decrease the number of connected components by 4, then we're going to be left with 1 connected component. So if we add another edge on top of that, we're going to get a cycle. So we want to connect all of these without creating a cycle because that's what a minimum spanning tree is. So our goal is to connect all of these with exactly 4 edges, but Prim's algorithm, or the definition of a minimum spanning tree, is also one more condition. We want to minimize the total cost of the edges. Now, I didn't actually draw all of the edges, all of the possible edges out right now. It would look something like this, right? Basically, for every single node, it could possibly be connected to every other single node. And the reason I'm not drawing it is, as you can see, it's going to get really complicated really quickly. So this is pretty much what it would look like if I drew every possible edge that could exist in this graph. And I think that's going to make it a little bit too messy, but let's just assume that those edges do exist, that for any point we could possibly connect it to another point. So the way Prim's algorithm works is we can choose to start at any single node in the entire graph, and then very simple, we're just going to perform a BFS, a breadth first search, on that node, where we are going to continuously for every node that we're adding, we're going to have 2 data structures. We're going to have a visit data structure to make sure that we don't add the same node twice, because if we add the same node twice, that's how you know we're going to get a cycle. We want to avoid cycles. The second data structure we're going to use is a minimum heap, which is going to keep track of our frontier of our breadth first search. Now, what is a frontier? Well, you might know that, let's say we had a single node. So we visited this. This is in our graph, right? This is part of our minimum spanning tree. What's the frontier then? Basically, every possible node that could be added from this position, right? So initially, if we just had one node, these 4 nodes would be in our frontier, but we're not just going to have each node in the frontier. So we're going to have, let's say node 1, and we're also going to add the weight of connecting node 1. So let's say the weight of the edge was something like 5, then we'd add 1, 5 in our min heap. But we're not going to add it in this order. We're going to add it in the opposite order, 5, 1, because when we're popping from the min heap, we're going to be wanting to pop whatever node we can connect next with the minimum possible cost. So let's say we had 5, 3, 2, and up here we have a 6 or something. Out of all these 4 nodes, which of them can we connect with the minimum possible cost? That's what we're going to use our min heap for. Looking at it, you can tell, okay, this one, because it has a cost of 2, so then we're going to connect that. So then that's going to be a part of our frontier. So next, we're going to say, okay, we have 2 nodes, a part of our frontier. Next, what we're going to do is add more nodes to our frontier. Even though we already had all 3 of these nodes, we're going to add them again to our frontier, because now possibly if we're starting from node 4 and we're trying to connect to 3, 1, or 2, it's possible that the connection from 4 to 3 or 4 to 2 or 4 to 1 could be smaller than the connection from 1 to those respective nodes. So we always want to connect a node with the minimum possible cost that it takes us. If it costs less to connect it to 4 than to connect it to 1, we're going to take the one with the smaller cost. And of course, as we visit nodes, we visit 0, we visit 4, we're going to add them to our hash set so that we don't, starting from 4, we're not going to go back to 1 and add 1 again, because that would create a loop. And how do you know that we can stop the execution of Prim's algorithm? Well, once the length of our visit set, the number of nodes that we've added, is equal to 5, which is the number of nodes that we started out with. So with all that being said, you just have to understand how these data structures are contributing to the solution, and then we can go ahead and walk through it. So let's start at 0. You can start at any node. You can start at 3, 2, 4, but in this case, we're going to start at 0 just because it makes sense. So when we start at 0, what we're doing is we're adding it to visit, and we're adding it to the frontier. So what's the cost of connecting 0? Well, if we're just connecting a single node to the graph, we're not actually including any edges, so the cost is going to be 0, and the node value is going to be 0. And so the way this algorithm works is at each step, we're just going to pop from the min heap. So let's pop the first value, this, right? So the total cost so far is 0, right? We don't actually have to add any cost. And that's actually one other variable we're going to be maintaining. Let me just write it down here. So far the cost is 0. We're going to continuously be adding to it though. But next, for 0, we're now going to add every one of its neighbors to the frontier. And the way we're going to add it, I haven't drawn it out, but there is going to be like an adjacency list. So we will have a list of neighbors for 0. Of course, it could be connected to every single point in the entire graph. That's just how this problem is defined. Now, I'm not going to write the exact cost of each of these edges, because I think it's pretty obvious from the picture that this is going to be the one that's closest, and the cost of connecting to that is going to be 4 based on the point values that we were given in the previous picture. So out of all these 4, these are going to be in our frontier. So all of these are going to be in our frontier, and you can see I drew them here. I didn't specify the actual cost of 2, 3, and 4, because I don't want to focus too much on that, because we know that this is going to be the minimum. So this is the one that we care about.
Okay. Import default dictionary, right? We're gonna have to create our adjacency list, right? So let's create some sort of function, right? We pass in, I don't know, let's just call it edges. It's not really edges, but whatever. we create our graph. Graph is equal to default dictionary, right? Okay, how are we gonna build this adjacency list though? I just don't know how we're gonna build the adjacency list. That's what I'm kind of confused about. You don't really have a node. These are points. We have to calculate the weight here, technically.
About right now because we already can tell from the picture that it's the smallest. And so that's the step, right? So you take the entire frontier, add it to the min heap. Next step, we're just going to repeat the same thing that we just did. We're going to take a look at our frontier, pop the minimum from it. We know that this is the minimum, so pop it. When you pop a node, we have to add it to visited. So we popped the one node, right? And so we're going to add it to visit, and the cost of that one was 4, right? So let's just add 4 to our total cost. So okay, so let's write it out. And like I said, so the first thing we're going to be doing is actually creating the adjacency list because that's not given to us. We're just given a list of points. So I'm going to get the number of points we have. And then I'm going to start creating that adjacency list. So, and basically I'm going to refer to each point in our list as basically the index of that point. So the first point in our points list is going to be point 0. The next one is going to be point 1, etc., etc. So we can just say for I in range of the number of points we have. So for I in range of n, the number of points, we're basically going to take each point I, map it to a empty list so far. Now we're actually going to build out that list. So for I in range of n, so for every single point, we want to compare it to every other point in the graph. So for j in range I plus 1 all the way to n. So we don't want to compare each point to itself.
Graph is equal to default dictionary, so then we would go, okay, well, for I in range length nums, for j in range I plus 1, the length of nums, right? We want to do our Manhattan distance, right? So we would do, okay, well, graph I dot append append really j, which would be our destination, right? And then it would be our weight here, right? And to do our weight, we do x. So then I feel like we'd have to do AB is equal to points I. This would be points. This would be points 2. Okay. Then we probably need to do like CD equal to points I, right? So then we would do, okay, well, need the absolute value of xi should be a minus c absolute value plus, oh, whoops, plus b minus d absolute value. But we're kind of appending a tuple here, right? So then we'd probably need to turn our graph. Graph is equal to adjacency list, and we pass in our points. Let's print our graph. Rock your body, rock your body, rock your body, rock your body. Why? What is wrong with this adjacency list? And had distances, but there's. Okay, they literally do the same thing as me, but they just like this is equal to, they do it here instead. Ah, in Python you can't do that. Okay. Abs A minus C plus abs B minus D. Ooh, minus D. Then here we pass in the distance. Well, since it's an undirected graph. Undirected, need both ways. Alright, so we would go graph. J dot append distance I. Okay, I just want to make sure this is good. There you go. Good thing I double checked it. Okay.
We just to get to the point pairing them, and we know we're basically going to have is going to be say adjacent distance, right? And the node itself, which is node J, so let's distance adjacency. Compute 4 is just a and I is basically a weighted edge. Don't forget about that. So we're going to say adjacency for I, append to it the cost or the distance, right? And the node itself, which is node J. And we're going to do the exact opposite because technically these are undirected edges. They go both ways. So let's just do the exact opposite. So adjacency of J, append to it the distance, same distance, but instead we're appending I because that's its neighbor. So this is how you build that adjacency.
Get cracked. Get cracked.io. This shit is so funny, bro. Like,
list, and technically we could actually not have to write this for loop out. We could actually, compute these calculations while we are running Prim's algorithm. But the reason I'm doing it before is just to give a clear distinction. This is the edge portion. This is like the extra portion of this problem. Okay,
so I think here what I have to do now is get rid of this print graph, right? We have our graph. We have to create a min heap, right? So we would need that. Okay. I feel like inside of our min heap, we'd probably need to start off with our first value, right? This is what we're gonna need. Shit, right, first value here. Okay, gonna need a visited set, right? So while there's something in our min heap, okay, but we need to import our first value, right? So min heap, right? We would want to start at 0, okay, and our weight is 0 technically, right? So here we'd want to pop, like we pop our weight and we pop our, I guess our node that we're at, right, is equal to yes, and heap dot pop, right? To heap q dot heap pop min heap, yeah, min heap, okay. Now to do that, we pop, we have to run BFS and check each of the other values, right? So we probably want to if node and visited, we probably want to just continue, right? Visited.add node, right? And then we have the BFS part, right? Where we would probably loop through each value. So we would go, okay, well, so for weight, for W2 and destination in graph node, okay, we would want to append it, right? So heap q dot heap push, we want to push to our min heap, and we want to push our W2 destination, right? This is where we pop, cheapest one, right? We have visitor.add, we need some sort of count, right? Count is equal to 0. Then we do, okay, when we add to visited, we want to also add our count, right? So we would add our weight, right? Then we do our BFS part, we add it, right? And then we will go back to the top, pop the smallest one, keep going, right? So, but where do we check? We have to check here. Well, if the length of our I guess, yeah, we want to have check in here. We check outside, right? Because now if the length of visited is equal to the length of points, sorry, we would just return count, right? If the length of visits is equal to the length of points, else what? Else, I'm just gonna put -1. I don't know. Oh. Oh, yep. Oh, slow.
Following part is literally just an example itself. So now for each neighbor, so for nay, we push the neighbor, and that's it, right? So we're
Okay, we forgot to add that line there. So if dest not in visited, right? then we push. It makes it faster, right? We don't have to go through, do everything again, which I think will increase our speed. Only by a little bit.
Just for every neighbor, all we have the exact same cost, space, and yet some pre-work that understanding necessarily related to Prim's algorithm. We do need an
I'll order like the fastest solutions to def root. Alright, we've been going for a little while now. Yeah, about an hour and a half. I think we'll probably do about one more problem here. Let's just jump into like some random problem. Like, I don't know. Let's give us like a random medium. See if we can solve it. Filter difficulty is, we want a medium. Man, some of these are really low acceptance, dude. Like, permutations 2. Why not, dude? Let's take a look at permutations 2. Given a collection of numbers, nums that might contain duplicates, return all possible unique permutations in any order. Well, I feel like this is definitely just a backtracking problem, right? Yeah. So, def backtrack, we want to keep track of our I, and we want to keep track of probably our current, right? We probably need a res, right? And we'd probably want a loop, so we go, well, if I is less than or equal to the length of nums, right? So if I is greater than or equal to the length of nums, okay, we want to res.append our cur, and we'd want to return, right? So this would be our base case. Okay. And we'd probably want to need some sort of well, we only want the length, the ones that, so let's do, well, if I is equal to the length of nums minus 1, then that's when we want to append, right? Right, because we go 1, 1, 1. Cur.append I, sorry, we would do backtrack I plus 1 cur.append nums I. Okay. Cur.pop. Then we backtrack I plus 1 cur, right? Right, because this won't work.
Because if we want all the different values, right? Just in different orders. I'm a little confused. Trying to think. Well, if we have a 4, we could start at I. We have a 4. Damn, dude. Okay, let's just see what we get here, and then we can. Do rock your body, oh oh, rock your body. Is that a pen code on copy? Bro, why is this not? Dude, what is going on here, dude? Oh my god, the function never gets called. Backtrack. 0. Then we have an empty car. Yeah, these are subsets, not permutations. know I have to use a for loop some way. I just like.
Hey everyone,
rather
welcome
visualize
back
what
and let's
someone
write
told
some
me.
more neat code today.
Talking it
So
through
today
me,
let's
know?
solve permutations 2, the follow-up to the first permutations problem. So we're given again a list of numbers, and the only difference with this problem compared to the permutations 1 is that this one actually might contain duplicate values. But we want to do the exact same thing. We just want to return all unique permutations in any particular order. So you look at this first example, right? We have duplicates. We have 2 1s. And if you don't remember, a permutation is that, okay, so we have 3 numbers. That means we have 3 spots. For each, so for the first spot, we have 3 choices, right? We can choose any of these 3 numbers. And if we choose one of the numbers, then we'll have 2 remaining. So for the next spot, we can choose 2 numbers. And if we do that, in the last spot, we'll only have 1 choice. So we know that we have 3 times 2 times 1 permutations, which is the same as n factorial, where n is the size of the input. But this is for a regular permutation, right? When you look at this, we don't have 6 permutations. We have 3. And the reason is because we have duplicate values in our input, right? So since this itself is one permutation, right? The list itself is a permutation of itself. One way we could get a different permutation is swapping the first 2 values, right? But if we reverse the order of them, we still get the same exact permutation, 1, 1, 2. And that does not count as a new permutation. It's a duplicate. It's the same as this one. So we don't want duplicates. I'm going to show you how to solve this problem with the difficulty that comes with it not having duplicates in our output. So we're going to solve this problem with backtracking just like the first one. And so this is going to be our input. So let me just show you why a normal decision tree with this is not going to work. So we know we have 3 spots, right, in our permutation. So let's say for the first spot, we choose the first element, right? 1. So that's 1 choice. For our second choice, we can choose this as the first element, right? 1, but we see that they're the exact same, right? This is what's going to cause our duplicates, but let me just show you why. The third spot will have a 2. So now for this one, we have 2 more choices, right? We chose the first one, but now we can choose either of these. So for our second spot, we have 2 choices. So we can do a 1 or we can do a 2. And if we did 2 1s, we know for our third choice, we can only do a 2. If we did 1 2, we know for our third choice, we have a remaining 1. And now let's do the same for this one. So we chose the middle one. So we have 2 choices, 1 and 2. Notice how we're getting the exact same result in both spots, right? So with this, we'll have a remaining choice of 2. For this, we'll have a remaining choice of 1. So along this branch, we had 2 different permutations, 1 1 2 and 1 2 1, right? That's our second permutation. And for this one, we had the exact same thing. We got both permutations duplicated, right? That's not what we want to do. And that happened because we started with the exact same value. We cannot use duplicates in the same position if we want to end up with different permutations. So this is a problem. Like, this solution just does not work currently. We have duplicates. We don't want duplicates. And so with the 2, actually, we'll also have duplicates, right? If we choose a 2, then we have 2 choices, right? We can choose either of the 1s. And then if we choose a 1, we'll only have 1 value remaining, a 1 for each of these paths. So now you see even these are duplicates, right? And that happened because for these positions, we chose the exact same value. So we can solve this problem, and the way we're going to do it is instead of using this array as our input, we're going to modify this array into a hash map. And let me show you what this hash map is going to look like. So this is our hash map. So we do not need this input array anymore. You can see we took each number. So we had a 1 in our original array, right? And how many 1s did we have? Well, we're going to count that, and we ended up with 2. And we also had a 2 value in our input. How many did we have? What's the count of that 2? Well, we only had 1. So basically with this list, we eliminated the duplicates, right? We only have 2 numbers. but we didn't get rid of it completely because we counted how many of each we had. So now with this map, I'm going to do the decision tree, the backtracking decision tree. So we actually have two choices now because look at the numbers that we have in our hash map. We have a 1 and a 2. So we have two choices for the first value, a 1 or a 2. So again, we're still doing the same thing. We're looking for permutations of length 3, right? And for our first spot, we're choosing either a 1 or a 2. So let's go with this path. So we chose a 1 for our first value. So now how many choices do we have? Can we only choose 2 in this case? Well, yes, we have 2, of course, right? But since we only used one of our 1s, right? So initially the count was 2, but now we used 1, so now there's only 1 left. So we're gonna have to update our hash map as we go along this decision tree. So we have 1 left. So now let's use that 1, right? So if we use that 1, then we'll have 0 1s left, right? So 0 1s along this path. And lastly, we'll only be able to choose a 2, which will leave us with 0 2s, right? So basically this is one of our permutations, 1 1 2. And you can see that this permutation is never going to be repeated because we cannot make that permutation again over here. We chose a 2 instead of a 1. And that permutation is never going to be repeated here because this one starts with a 2. It does not start with a 1. So now let's finish up this decision tree because we know we cannot add any more to this. It's length 3. So these counts are getting kind of sloppy, but I don't think I pretty much have used them to illustrate what I wanted to. So lastly, we know that there's only a 1 left over here. So this is also going to be a permutation. So far we have 2 permutations in our left subtree. Now let's finish up the right side. So since we started with a 2 over here, that means we ran out of 2s, right? We have 0 2s left. But in reality, we have 2 1s left, right? Because we only used a 2, we have 2 1s left. Does that mean we have 2 choices? Can we choose 1 on each side? No, because look at the unique numbers we have. This is our only number left. We've used up this one, so we have 1 choice in reality. So we can choose a single 1. And then the 1 count is going to be left as 1. So we have 1 remaining. So we do have a choice left, but it's only a single choice and it's going to be a 1. Let me just make these green. So now you can see that we ended up with 3 different permutations. And basically we eliminated the duplicates by transforming our input array into a count hash map. Okay, so now let's get into the code. So we are going to have a result, which is going to store the list of permutations, right? The output. And we're also going to have a list to store each permutation itself. So we only have 1 variable to do this. And lastly, let's make our count hash map. So I'm going to take each number and initially map it to 0. So for every number in our nums input, I'm initially going to map it to 0. So the count is initially going to be 0. Then I'm going to go through every number and update the count of our map. So for every number, we're going to increment its count by 1. So with this, we'll have a count hash map mapping every number in the input nums to its count. And then all we have to do is create our depth first search backtracking function, and I actually don't even need to pass any input values into it because all of these values are going to be accessible inside of here because this function is nested inside of another function. So in this case, for this function, our base case is going to be that our permutation that we have, the length of that permutation is equal to the length of our input nums. That means the permutation is a complete, right? We have no more values left to choose to add to the permutation. And once that's the case, to our result, we're gonna append a copy of the perm list. And the reason we're making a copy is because we only have one of these variables. Every time we make a change to it, we're gonna end up updating the variable. And since this is our base case, after that we can return. So next, we're gonna brute force this, right? We're gonna choose every choice that we can, and what that means is we can go through every number in count, right? Count has eliminated the duplicates. Every key in our count hash map is going to be unique. And for this value, we just want to make sure that the count is greater than 0. That means we're allowed to choose this for a permutation. We have enough values left. And we're going to take this value and add it to our current permutation. And if we add it to our current permutation, we have to take the count of it and decrement it by 1, right? Because we're now going to recursively call depth first search again. And once that depth first search is completed, it will probably have, gotten to its base case and ended up returning. After that, we can then clean up, meaning we can take the count of the value and add it and add 1 to it, right? And also then take our permutation and pop from the ending. So basically remove the value that we just ended up adding. And so this is going to ensure that we do not have duplicates, and we also end up getting every single permutation, which is why we're going through every single number in our count hash map. And lastly, since our depth first search function is complete, we only have to call it, and then we know our result will have the correct value, so we can then return our result. And as you can see, this is about as efficient as you can get for this problem, even though this is super brute force. I don't even know what the time complexity is. It's at least, I think, O of n times 2 to the power of n, because 2 to the power of n is
the res is equal to the length of nums. Alright, then we just want to res autopen code.copy. Alright, return. I think, can we do like a nums.sort? We have our res. We loop through. For I in range length nums. I don't really like that solution that Leetcode did. It's not really intuitive to me. Like, I would have never really thought to use a hash map here. Like, to do this and to think about this using a hash map, I would have never really thought about this. Looping through each value, checking if the count. So we perm.append that number, right? We decrement, we call DFS, and we come back and we keep selecting, right? So here they expect us to make a use array that has false for everything times the length of nums, right? And we loop through. This is our base case, right? And then our recursive case, okay? We loop through this and we check, okay, well, if used I, right? If it's true, we just continue, right? We've used that number, right? Otherwise, we check, well, okay, well, if nums I is equal to, sorry, if I is greater than 0 and
nums I is equal to nums I minus 1 and not used I minus 1. We have used I is equal to true, code append nums I. Alright, then we call our backtracking function, I plus 1, cur. Right. Back, we'd code up pop. And we do use I is equal to false. So we don't even need this I plus 1 anymore. We're not using a floor now, so. I don't see it. There's one bug. Oh my god, that's why. This needs to be length of cur. I want to take a look at the other method, the dictionary method, the one that minus code dictionary is equal to this, right? So then we go, okay, well for I in range length nums, right? We can do, okay, minus code I is equal to this, right? And we can do, well, for I in nums, sorry, for I in nums, if minus code dictionary I plus or equal to 1. We need to do, okay, for I in nums, dictionary I is equal to 0. I mean, same thing, right? Okay, then we do our backtrack, right? We don't need to pass in anything. So do okay, so if I in count I in my dictionary, if count I is greater than 0, right, then we take that thing, right, we perm.append I, and then we call the DFS function. So we'd have to do, okay, minus code dictionary. Dictionary I minus equal to 1, right? We call our DFS function, right? Then we'd have to, not perm, sorry. Code.append I, call our DFS function. Then we'd have to do code.pop, and then minus code dictionary I plus or equal to 1. I mean, it doesn't really matter the way, but I'll just switch it around anyway. Right. Then we would call backtrack. There we go. Alright, fair enough. Okay, we'll call it there today. That was a good problem. Good to think about that again. But I appreciate you guys watching, and I will see you tomorrow.